Hi, welcome back to Drafting 112, Beginning and Intermediate AutoCAD at Blue Mountain Community College. We're going to talk today, we're going to continue in this week with Chapter 7. And Chapter 7 is all about tolerancing and fits. And so we're going to start by understanding basic tolerancing nomenclature. And then we're going to talk about some designations and some standard fits. And we'll close up with looking at how we do tolerancing in AutoCAD. So tolerancing is really how we tell the machinist and the manufacturer how precise these measurements need to be. No measurement is ever going to be hit exactly that same number. There's always going to be some allowances for tools or calibration, but the tolerancing is how we designate how precise, what the acceptable limits of these measurements are. So for example, if we look at this little, just a sec, there we go. If we look right here at the distance between these two holes, we see two different dimensions shown. We see 1.750 and 1.745. What that means is that as long as that center-to-center distance is between these two values, then that part is acceptable. So we have a tolerance of 0.005 between the acceptable limits. There are different ways to indicate the tolerance on a dimension. You can do it with a plus or minus a fraction, like plus or minus 1/64th, which would mean that you'd have a center value, and as long as you were within 1/64th of on either side of that, you're acceptable. You can have decimals, as in the center value, and then plus or minus a 0.01, or the center value plus or minus 0.001. Angles typically are almost always going to be plus or minus, or you can have it designated this way, with smallest to largest. This is what we call the limit method. What we're doing is we're specifying the limits, the limits on the acceptable size range. We can also have a bilateral specification, which means it's the basic size, and then how much bigger our dimension can be than that basic size, and how much smaller our dimension can be than that basic size. So, and those don't have to be symmetrical. In other words, we can tolerate a bit bigger easier than we can tolerate closer together in this particular example. General tolerances. So on that drawing that we started with, and this is pictured, that same drawing is on page 7-2 in your textbook. If you look at that drawing, you'll notice some dimensions have specifically called out tolerances and some do not. If a dimension does not have a specifically called out tolerance, then it'll be subjected to the general tolerances that are shown in a box to the side of the drawing. These are the tolerances that will be enforced unless something else is stated. It's like the unless stated otherwise disclaimer we see in a lot of different places. If a tolerance has been applied on the drawings directly, it will override the general tolerance. Okay, so the nomenclature you need to know. You need to know what the nominal size is. That is the base size, the 3.75. Actually, it's not. The nominal size is like on pipes. If you buy a 2-inch pipe, you know that there's no dimension about that. That is 2 inches. That is the nominal size. It's a designation used for general identification. The basic size or the basic dimension is the theoretical size from which limits are derived. That is usually it'll be the dimension to which the plus or minus is applied. Actual size is what you actually get after you make the thing. Fit is kind of like a classification of tightness of tolerances, and we'll talk about that some more in a minute. An allowance is the minimum clearance space or the maximum interference. Sometimes you want parts to interfere with one another. And we'll talk about that. And it's under something called you'll either have maximum interference or maximum material, and we'll talk about both of those things. Tolerance is essentially the length or the difference between largest allowable and smallest allowable. Now let's talk about the maximum material condition. This is a little tricky. It's essentially the size that has got the most material remaining. So if you think of like a hole, holes are a little weird because the maximum material condition is the smallest allowable hole, whereas if you've got a shaft, the maximum material condition is the largest allowable shaft. So we'll talk about that some more. The least material condition is kind of the same thing, except it's the condition or the size of the combination of allowable dimensions that result in the smallest amount of material being present. So let's look at this part we've got drawn here. We've got both the hole into which the shaft, so we've got the hole into which the shaft is going to be placed and the shaft itself. And there's a lot of information on this slide, so we're going to spend a little time here. So what we've seen is the hole can be between 1.125 and 1.127 inches. That means we've got a tolerance of 0.002. The tolerance is the largest allowable dimension minus the smallest allowable dimension. So this thing has to be machined to within 2/1000ths of an inch. The shaft can be between 1.124 and 1.112, which means we've got a shaft tolerance of 3/1000ths of an inch. So the overall allowance is the maximum material condition hole. If we think about what that means is at the most allowable material left, which means the smallest allowable hole, which is 1.125, minus the maximum material condition shaft, which is the largest shaft, which is 1.124. So we've got an allowance between the hole and the shaft of 1/1000th of an inch. The loosest fit is really exactly the opposite. It is the largest hole, which is the least material condition, minus the smallest shaft, which is the least material condition. So that would be 1.27 minus 1.121, which is 6/1000ths of an inch. Clear as mud? Hopefully clearer. Okay, so this is example 7.1. And what we want to do is we want to figure out the nominal size, the tolerance of the shaft, the tolerance of the hole, the allowance, and the maximum clearest parts. So I encourage you to pause this presentation, this video at this point. Write those things down before you go on or look at the book to see if you have an understanding. So it's kind of a self-test for yourself, a self-check. We're going to go on now and look at the answers. So for this shaft, the nominal size is it's the closest regular dimension. So we're going to call this a 1.25. It's a 1¼ inch. The tolerance of the shaft means the maximum shaft minus the minimum shaft. Okay. The tolerance for the hole is the largest hole, the difference between the largest hole and the smallest hole. the allowance between the two, the allowance is going to be the smallest hole compared to the largest shaft. Think of this as the closest fit you're going to get. And the maximum clearance is exactly the opposite. It's the biggest hole compared to the smallest shaft, so it's going to be the biggest difference you're going to get. Okay, let's now talk about some standard terminology. And we are on page 6. Believe it or not, we've only done 6 pages. We're going to talk about a clearance fit. A clearance fit is a condition in which the internal part is guaranteed to be smaller than the external part. There's always some space in between them. So the smallest hole, largest shaft, everything will still fit as long as both parts are within allowed measurements. Okay, an interference fit means that there's going to be some interference. That shaft will not ever fit into that hole. So the smallest hole is, or the largest hole is going to be smaller than the largest shaft. So there's always going to be an interference. It means you never want that shaft to go into that hole. Okay, a transition fit is somewhere in between those. There's going to be some pieces which will fit in that hole. There's some pieces that won't. So when we're doing selective assembly, if we specify our tolerances correctly, things will always go together. This is really good for machine assembly stuff. But if we do something like a transition fit, that means some shafts will fit in some holes, and it requires real selective assembly of pieces. Generally speaking, your assembly costs and your manufacturing costs are going to be the lowest when you can guarantee that any shaft will fit in any hole. So pieces will always fit together. Okay, we haven't talked too much about standards in this class, but we're going to now. And so ANSI, ANSI, is the American National Society of Limits. I can't remember. American National Standard Institute, that's what it is. So we're going to talk about ANSI, or ANS, limits and fits. This is for inches. So if you see something that says RC, that means it's a running or sliding clearance. And what we want to do is turn to Appendix A in your textbook. So if you don't have your textbook out, pause this video and go get it. Get it and open it up to page A-1. It's at the back of your text after chapter 12. And it's an appendix that talks about running and sliding fits. And you'll see that what it gives you is RC 1 through 4. In general, if you look at what this information says, so let's say we've got a hole, and say our hole is 1 inch. What you want to do is look down the left-hand column. There is the 1, 2, 3, 4. The left-hand column talks about the nominal size range in inches. And the 5th cell down, 5th row down, has got 0.71 to 1.19. 1 inch is in between those two numbers. And so if you've got an RC1, that means that your limits of clearance will be between 0.3 and 0.95 inches. So your hole is going to be, your tolerances will be plus 0.4 minus 0. Your shaft will be minus 0.3 to minus 0.55. So you'll notice that there's no pluses on that shaft. And you can see that as you go further out, the limits get larger on running fit. So what running or sliding means is it means that those things will slide freely next to one another. And you can have different levels of running fits. And if you turn the page to A-2, you can see that goes clear out to RC9. And this first table is for inches, the next one's for millimeters. And then we move into location clearance fits. What you want to do is make sure you understand what each of those different types of fits are. And they're described in your text beginning on page 7-8. All right. So what you need to understand, what we need to be able to do at this point is know the difference between a basic hole system, or right, you know how to use a basic hole system. So let's work through this example. We've got a design that requires the use of 2 mating parts, and the nominal size is 0.75 inches. We're going to run a shaft with moderate speed, but fairly heavy journal pressure. We want the engineer has specified fit class of basic hole system R6. And our job now is to, as drafters, note the allowed tolerances on the machining diagram. So we go to our Appendix A, Table 1, and find RC6 for a 0.75 inch nominal size. That's going to be actually that same row we were just talking about. Read over to the right until you get to the RC6. What we see is that we have limits of clearance of 1.6 and 4.8. And notice those are not in inches, so be careful with these. If you read up at the top, very top of the page, right under the title, it says limits are in thousandths of an inch. So what this means is 1.6 thousandths to 4.8 thousandths. Plus 2 1,000ths of an inch minus 0 1,000ths. Minus 1.6 minus 2.8, 1,000ths of an inch. So this is 0.0016. Okay, the basic size is 0.75, which means that my maximum shaft size is going to be 0.75 minus the smallest allowed tolerance, which is, which is 1.6. So 0.75 minus 0.0016 means my largest allowed shaft is 0.7484 inches. My minimum shaft size is 0.75 minus the largest allowable tolerance, which is 0.0028, 2.8 thousandths of an inch. So 0.7472. Okay? The hole would be figured as my basic size, which is 0.75, plus the 2 1,000ths, 0.002, or the largest hole would be 0.752. So my tolerances on my hole would be 0.752 to 2.75 inches. All right, just like we have right here. So now we can do the same calculations we did a few minutes ago to look at tolerances of the shaft and the hole, the allowances, and the maximum clearances. And if you notice, those maximum clearances that we calculate match up with what's in that table. So the allowance and the maximum clearance are the limits of clearance indicated on the table, the 1.6 and the 4.8 thousandths. Okay, now things are a little different. We can either, that's a hole system. That means our hole is the 0.75. Our tables are all based on a hole system. Sometimes you want your shaft to be the basis. And so then what we have to do is we have to convert from the basic shaft system to the basic hole system. And actually what we do is we convert the table rather than the dimensions. And this next slide will walk us through doing that. So we've got this same row showing the same information, but remember that previously we were basing this on the hole being the 3/4, the basic hole system. Now we want to use our shaft as the basis of our measurements. So what we're going to do is add 1.6 to all of these dimensions. So what we're doing is we're taking this largest shaft and making it be the 0. And we do that by adding this number, whatever it might be. In this case, it's 1.6. We add the 1.6 to negative 1.6, we get minus 0. 2.8 minus 2.8 plus 1.6 gives us minus 1.2. 2.0 plus 1.6 gives us plus 3.6. Plus 0 plus 1.6 gives us plus 1.6. So what we've done is we've made sure that our shaft, our largest shaft, is the 0.75. For the basic shaft system, it's going to be our largest shaft, that is the 0. For the basic hole, it will be our smallest hole, that is the 0. Hope that makes sense. Okay. So now we just do the same calculations based on the largest possible shaft being 0.75 inches. Okay. We have the same basic ideas when we're working with metric systems. We just have to use different tables, and we use international tolerance grades instead of fit classes. And there are 18 of those. IT01, IT0, and then IT1 through 16. So 0, 1 is different than 1. Okay. Same basic idea. You either use a hole basis system or use a shaft basis system. H, uppercase h, indicates hole basis. Lowercase h indicates shaft basis. So 30H8, where the H is capitalized, means my basic hole is 30 millimeters, and my hole size will be the basis. And we'll use IT8 class for tolerances, and you can find the information for the IT class also in Appendix A. I believe? Okay. Now, there's also an F, and that is it's a further designation on the fit. And you can find all of this information in your textbook. There it is. On page, starting on page 19, it talks about, there's a table that tells you about the preferred isometric fits. I'm going to leave that for you to read. It's pretty much all the same. And there's that table I was just telling you about. And there's an example, 7-6, which is on page 7-20. It's on page 20 in chapter 7. Walks you through this. It's all the basic same concepts as we were just talking about with the English system, just that now we're using millimeters instead of inches. So I'm going to let you read through this, and I'm going to stop talking for a little bit. We will build on the drawing that we did in chapter 6, that bracket drawing, to add some fits. So I hope you saved it. If you didn't, you'll get more practice. All right, I will see you again soon.